Daniel will tell us about scaling trustless deep neural network inference with ZK-SNARKs to GPT, ResNet, and beyond. Well, thank you, Daniel, and let's hear it.
Great, thanks for the introduction. So thanks everyone for coming to the final talk of the session. I know that this has been a long day, and hopefully this talk will leave some time at the end to allow people to get a bit refreshed before the end, and also to answer some questions. So today I'll be talking about scaling trustless DNN inference to these larger models, including GPT, ResNets, and others as well. So if you've been following the news over the past few months, you'll probably know that ML is eating the world and we'll all be unemployed soon. So things like ChatGPT, Bing Search, and Google Bard are becoming increasingly prevalent. And also things I'm not mentioning here, for example, Midjourney and Stable Diffusion have shown amazing results. And so one question I want to focus on today is, can we execute machine learning models trustlessly? I'll motivate this with a few applications, but before that, I want to talk about some stuff which I realized after I made the slides this audience probably knows a lot about, so I don't really need to cover it. But there's a variety of ways to do trustless execution, including multi-party computation, homomorphic encryption, and zero-knowledge proofs. And obviously, we'll focus on the zero-knowledge proofs today. And so some of the features that are obviously really great is that they can give privacy, validity, and no interaction. But unfortunately, they have high compute overheads. So I'll describe some techniques on how to reduce this, specifically for ML models and also for image edits, which is important for certain kinds of applications I'll talk about today. Also, very boring for this particular audience, but I just want to be a little bit concrete about what's going on here, since I'll use this notation later. The prover takes in some private inputs W and some public inputs X and produces a proof. This proof can then be validated by any verifier after the fact. And what's also really useful is that these proofs can be computed after the computation is done, which again is very important for certain kinds of applications I'll describe later. So I promise that I'll motivate the need for executing ML models trustlessly with several applications. And I'll first start with trustless audits. So why do we care about this? Well, as ML increases in the different uses and scenarios, we want to be sure that the models that we're running satisfy some properties. For example, for medical ML, you might want to ensure that the training data set conforms to some regulations, for example, by the FDA or some other regulators. And also recently, Twitter open sourced their algorithm, and you might want to ensure things like my timeline isn't biased. But of course, Twitter has a bunch of private user information that they are not allowed to release due to regulatory reasons. But they still might want to show that certain properties like this. So how can we accomplish this with ZK-SNARKs? Well, we'll use two steps. The first step here is the proof of training, which unfortunately also has two steps. The first thing to do is to commit to the training data. And so, for example, you might want to commit to the images you're using for training a medical ML model. And then you can, in fact, unroll the entire training process. One common method of training ML models is using what's called stochastic gradient descent. And you can produce ZK-SNARKs of the training process to ensure that the model that can be committed to at the end in a hiding manner was actually trained on the data that you committed to originally. Then you can compute these audits trustlessly. And in general, these audits take the form of a function of the data and the weights. And in particular, all of these can be hidden using the process I described in the previous slide. And as I mentioned, there's many different kinds of audits that you might want to run. For example, that your data isn't biased for medical ML, that your model performs well, also, for example, for medical models, and say that your timeline isn't biased, and a whole host of other things that consumers might want to know about the models that they're consuming. Another important type of audit might be that your training data doesn't contain any copyrighted images. I also want to talk about two other applications before I go into our open source framework. And I'll first start with decentralized prompt marketplaces. Just to get everyone on the same page, there's been a huge boom in generative AI in which you take in some inputs. In this particular example, it's an astronaut riding a horse. You pass it through some complex model, and then out comes an image or a piece of text or audio or some other thing generated by an ML model. Now, this particular prompt is very simple, but there's a whole host of other kinds of prompts that you might want to use. So let me try to read this. Cinematic, off-center, two-shot, 35mm film, still of a 30-year-old French man, curly brown hair, and a stained beige photo. Anyway, you get the point. These prompts are complicated and, in fact, require a lot of effort from individuals to create. And they're also very valuable. Now, if you try to reverse engineer, for example, this one, this is my best attempt at this. Clearly, I'm not very creative. But the point I'm trying to make is that these viral images that are generated from these amazing generative AI methods require a lot of effort to create. And I want to put a number on this, actually. Prompt engineers can pay up to $335,000 US per year just to generate these prompts. Now, I'm not going to make any commentary on this, but you might want to imagine that there are very valuable things you can do, but you might not want to pay for an entire engineer to do this. So instead, what you can do is produce these, what I'll call proof of prompts. So to do this, you can take in the inputs, which can be hidden, as I described earlier in this talk, and produce a ZK-SNARK, which generates the output. Now, one thing that I might want to do is that, let's say I want to do some marketing based off of that looks something like this. I can then purchase this prompt, which the user can then reveal to me, and then I can modify it to set for my own particular use cases. For example, I might want to have a diverse set of prompts for different kinds of backgrounds to target to specific demographics. And ZK-SNARKs will enable this in a decentralized manner. The last application I want to talk about is trustless biometric authentication and also fighting deepfakes. And this is the application I'm personally very excited about. So first, what are deepfakes? Well, deepfakes are images or video that modify what a person looks like, and specifically for a malicious purpose or to spread misinformation. I want to contrast this with the harmless forms of generative AI, like I showed in the previous slides. In the opening session of today, ZKpod.ai was mentioned, and this is an example of a positive use, but you could also imagine taking Anna's voice and making her say terrible things. And you might want to be sure that she doesn't actually, Anna might want to prove that she didn't actually say these things. Now, unfortunately, with the rise of generative AI, deepfakes are also on the rise. The things I'm listing here are actual uses of deepfakes that have been already used today. They've been used by state actors to spread misinformation, to trick businesses into miswiring funds, and even fool unsuspecting consumers into being scammed. This is one example of ftxcompensation.com, which I do not recommend visiting. Okay, so to fight deepfakes, there's many parts of the technology stack that need to do to enable this. And one of the things I want to tell you about is these things called attested cameras. Now, attested cameras contain hardware devices in them that sign the pixels that come off the sensor immediately upon capture in a trusted way. And after you have the signature, it can attest that it took a specific photo, but say not a deepfake. Now, of course, attested sensors are great for this very particular operation, but there's unfortunately many things it doesn't help with. In many circumstances, the taker of the photo wants to edit the images privately. Now, one obvious example is that you might have this very valuable credit card that you want to crop out before releasing the photo. But also, even for biometric authentication, if you take a photo of yourself, say a selfie, it might contain extraneous information, and you might want to crop down to the specific part that contains your face. But also, if you want to do this in a privacy-preserving way, you can't reveal the original image. Now, to address this, I developed ZK-Image, which can attest to image edits securely and privately. And the way this works is that given the signature or the commitment to the original image, ZK-Image can take this as a hidden witness and then output a and output the image, an edited image that's done using ZK-SNARKs, so that the consumer of the photo can verify that the edits were done honestly. For example, that I didn't run an AI method that swapped out the face. So I mentioned that attested cameras themselves don't solve the problem, and neither does just ZK image. ZK image needs to also be combined with other kinds of technologies, for example, decentralized ways of tracking these signatures. And so, for example, you might have a registry which contains the signatures of the original images and the proofs. And whenever someone wants to consume the image, they can then consult this registry. You also might want to attest to multiple edits, and in order to do this, you might have to use multiple proofs. I won't get into the technical details today. They're described in our preprint on archive, which you can find on my personal website. I also want to talk about how to do trustless Face ID using these technologies. So the first thing you do is you can take a photo of your face using an attested camera, and you need this to validate that the photo actually came from the real world. And then you perform some image edits, for example, cropping the photo to only contain your face. You might also do other things like rotating the photo or sharing it to be better for the next step, which is to input it to a Face ID model. And then by combining these steps, you can then produce a proof that, say, your face embedding matches one that you uploaded previously. And this can all be done privately without revealing sensitive biometric information to service providers. Great. So now that I've talked about the various applications of ZKML, I want to talk about the open source framework that I just released yesterday and what it can enable. So if you look at the frameworks for zero-knowledge proofs on some of the prior work, all the prior work operates on these unrealistically small images. For example, on these data sets, which are very common in ML, like MNIST or CFAR10, which are these tiny images which are really used for just toy demonstrations of capabilities. And with our framework, we can scale this to ImageNet, which is a realistic sized data set that's actually used in, where models of this form are used in production, and also other models, which I'll briefly mention, like GPT, and diffusion models like the generative AI things that I mentioned earlier as well. So in order to produce our framework and produce these ZK-SNARKs in an efficient way, we need to make many design choices. And this ranges all the way from the ML side straight down to the proving stack. And this includes choosing the correct architecture, arithmetizing the DNN computation efficiently, and leveraging the proving system in such a way that you get high efficiency. From an architecture perspective, we use quantized models, and we do it in such a way that we can achieve high accuracy despite doing the quantization. I'll briefly talk about this later in the talk, but just to give you a sneak preview of results, using our quantization methods, you lose something like 0.02% accuracy compared to some other frameworks and other libraries that lose a lot of accuracy when doing quantization. We also have to optimize the arithmetization, which is basically how the circuit is laid out, and use the proving stack efficiently. I won't go into the technical details. I'm sure everyone here is tired after a long day of staring at math all day, so I'll just briefly talk about what we do. We do the linear layers efficiently using custom gates with these polynomial constraints. The non-linearities via lookups, and we do some tricks with the fixed point arithmetic to be a little bit more efficient compared to just doing the operations naively. So to use ZKML, all you need to do is install Rust, clone our GitHub repository, and run our example. And in this example, we have an MNIST model which achieves 99.5% accuracy, and this will actually run on your laptop. And it runs in about 4 seconds, which, as far as I'm aware, is the most efficient proving of an MNIST model that achieves over 99% accuracy. But in addition to that, I also want to talk about the evaluation of our framework, ZK-ML, on realistic models. And what we'll focus on in particular are these things called mobile nets, which are also used in production. In fact, many of them are running on your phones today. So in the paper that I published on this earlier last year, we can achieve around 79% accuracy on ImageNet with proving times of around 2,500 seconds and verification times of around 10 seconds. With our open source release, we can get, this is a bit outdated actually, we can get 13% higher accuracy, 6 times cheaper proving, and 500 times cheaper verification. And all the applications I described earlier really depend on the efficiency of being able to run these to compute these ZK-SNARKs in a reasonable amount of time. And we're working really hard to ensure that this is accessible to everyone, not just the most powerful servers in the world. Now, just to give you an example of the improvements, let's say you want to use our framework to verify a private model's accuracy. These are the costs with our previous work. But with our new work, and this is the cost of proving, we can take down the cost of verifying a model's accuracy within 1% from around $2,500 to about $400. And just to put this in context, for a medical data set, it might cost around $85,000 to produce the labels for this. So verifying the accuracy is becoming increasingly feasible, especially in comparison to how much the training data costs to obtain. So as I promised, I think we're ending a little bit early, so plenty of time for questions, but also to relax after the talk. But in conclusion, we're increasingly interacting with digital systems, and zero-knowledge proofs provide trust in the face of adversaries, and this includes for ML models and also against deepfakes. We just open sourced a framework yesterday. The link is available down here. My email is here, and my Twitter is here as well. I'm happy to be contacted offline if you have any questions, but I also think there's some time for questions now as well. Thank you for coming to my talk.
Thank you so much for that talk. Are there questions, thoughts, comments? And actually, if you have a question, just put your hand up so I spot you.
Hi, welcome. I read your previous printed version. Actually, I asked a question on the Telegram. So I'm curious about the improvement, this huge improvement of the proving time and the verification time is given by, let's say, a Hello tool or given by anything else. You have some specific trick or improvement on that?
Yeah, so the question was about where these improvements come from. There's a number of things we did to improve the performance. For the verification times, we allow both IPA and KZG has much more efficient verification. We also have many improvements in the actual arithmetization of the circuits, the way that we do the fixed point arithmetic to increase the accuracy, and also some algorithmic improvements on how to do, say, convolutions and matrix multiplies more efficiently. We'll have a blog post detailing all of our improvements in the upcoming weeks. So be on the lookout for that. I'll announce it on my Twitter, and also happy to, if you contact me offline, I can provide some more follow-ups as well.
All right, Guillermo, you go first.
So quick question. You mentioned that you could potentially do provable training, which seems particularly difficult, right? Because provable training requires that you try a bunch of seeds and do a bunch of like different stuff. Like it's a little bit more of a dark art than just inference. So does this framework currently support like provable training, or is this just like a thought exercise at the moment?
Yes, the question was, do we support provable training? The answer is yes, actually. We have results that unfortunately came in after the slide deadline. So they're not here, but be on the lookout for the blog post. Roughly speaking, so training has many complexities beyond inference, as you mentioned. So it's a little bit more difficult. With our preliminary results, we can achieve nearly the same accuracy as full floating point 32 precision using our framework, and also at reasonable cost relative to the cost. relative to the cost of the labels on this data set. And be on the lookout for that. There's actually, if you look hard enough, you'll be able to find it in our repository, but it's not ready for public consumption yet.
Thank you.
Thank you so much for the talk. I was actually also going to ask about training, because I read a paper recently, and it said that you can embed an adversary example in a network, and it will be undetectable, but they will always be able to provide an output they would like to get from the network. That's why I think training would be very important to be verified if you want to actually use the ZK proof of inference. My other question is, you mentioned that the loss of precision is very little because of quantization. Do you have the numbers for GPT? Because I also know you did GPT-2 proving. Do you have numbers of how much of a loss was there?
Right, so there's two questions here. The first is about training and planting backdoors. I believe you're referring to the Shafi Goldwater paper. We can avoid this, we can literally provably avoid this through some mechanisms which, basically, once you commit to the training, you can do this in a way that the commitment, and you can basically base the data traversal order based off of your commitments in such a way that the trainer cannot mess with it. So this prevents those kinds of backdoors that are specific to that paper. In terms of your other question, accuracy on GPT, that is a great question. Unfortunately, accuracy for generative models is much harder to measure for many reasons. But if you compare the outputs of our framework compared to the outputs of using floating point FP32, so full precision, we have like an error in the vector outputs of maybe like 1% or something. So we don't think that there's going to be a substantial loss in accuracy. And we're also actively working to bring this number down as we improve our framework. So happy to talk offline about that as well.
Thank you very much.
Great. There's a question back there and one over here.
Hello, thanks for the talk. I was just wondering, in the case of the generative models, where you've got some randomness that is used to generate the response, is there a way to prove that it's truly random value and that the model hasn't been run many times? Or is there a hope of a solution to that?
Yes, the question is for generative models, there's often some randomness that needs to be input to the model. And if there are ways to ensure that the randomness wasn't chosen in some adversarial manner. The answer is actually yes, although it's not necessarily within our framework. There are several things you can do. So one thing is that you can use the verified randomness, for example, from the Ethereum beacon chain as inputs to a pseudo-random number generator to generate the randomness. And you can prove the pseudo-random number, and you can do the snarking of the pseudo-random number generator to verify that you can't, that the producer of the generative output didn't cheat. And one way you can do this is you can say, okay, you can commit ahead of time that I'm going to use like the randomness from the block like 1,000 blocks from now, so it's hard to cheat. And there's other ways you can do this as well by using other forms of verified randomness. For example, you can hook up to random.org if you trust them, and other kinds of techniques as well.
Oh, wait, there's one up here, actually, that was first here. Oh, you're going to go around.
In practice, how high an assumption is it to trust that the sensor produce authentic data, such as Face ID or a camera that signs the input?
Yes, the question is, in practice, how much can we trust the attested sensors? And this is always a work in progress, but I think that as this problem becomes more and more prevalent, the public desire for these kinds of things will increase, and so will the security. So, in some sense, there's no way to fully block against physical attacks. Like, if I'm willing to pay enough money and wait enough time, I can get plastic surgery to look like someone else. But we want to raise the cost of performing these kinds of attacks beyond being able to do this entirely in software. And that's the hope, especially as these technologies advance, as people realize that generative AI can be very dangerous in addition to being very useful.
I see a question over here. Yeah, if there are any last questions, just put your hands up now so we get you.
Thanks very much. Very impressive work. Do you have already plans on improving further? I mean, not to be demanding, but maybe recursing or aggregating or folding even. Is this things you're thinking about?
Yeah, so the question is, are there plans to improve? It's a hard audience over here. No, sorry. We have many plans to improve. There are things, there are optimizations ranging from the proving stack to like aggregation, for example, for training in particular, to optimizations on the deep neural network level, and also just on the basic computer systems level to improve the performance of our framework. And that's in the works. I'm happy to chat about the specifics offline if you want to get into nitty-gritty technical details.
Perfect. Seems like that might be our last question. Thank you so much, Daniel.
Thank you.